When evaluating the medical efficacy of functional foods, researchers typically target one of two distinct physiological environments. First, the localized gastrointestinal tract for managing conditions like irritable bowel syndrome, and second, the systemic pathways, aiming to mitigate neuropsychiatric issues like oxidative stress and depression. These two biological environments operate under completely different chemical rules. Treating an inflamed intestinal wall requires a localized intervention, while neutralizing oxidative stress at a neural synapse demands compounds that survive digestion to enter circulation. Currently, one botanical subject is being heavily studied across both fields simultaneously, Musa paradisiaca, commonly known as the agung banana. Before undergoing physical processing or human digestion, its raw biological matrix contains a highly specific set of starches, phenolic compounds, and amino acids. A common clinical error is assuming that this baseline phytochemical profile acts as an inherent, static medicine, that the plant is simply good for the gut or good for the brain by default. In reality, physiological utility is governed by the physical state of the plant tissue. The ripening timeline dictates how the pulp ferments in the gut, while extraction parameters applied to the waste biomass limit what molecules survive the process. Treating organic material as a static cure leads to clinical failure. To determine if this plant actually works as a medical intervention, we must analyze its precise biochemical matrix at specific stages of maturity and extraction. We will start by examining the local gastrointestinal environment and the internal matrix of the banana pulp. The key component here is resistant starch. Unlike standard starches, which are rapidly broken down into glucose by amylase enzymes, resistant starch possesses a unique molecular structure that physically resists digestion as it passes through the small intestine. This chart tracks the molecular shift as the banana ages. You can see two inverse trend lines. Resistant starch breaks down and drops, while fructans sharply increase. At the early green stage, we find the highest resistant starch and lowest fructans. When high volumes of resistant starch reach the large intestine intact, it acts as a prebiotic. It undergoes a very slow fermentation process, which produces short-chain fatty acids that support a healthy colon environment. This bacterial fermentation is highly gradual. The microbes slowly dissolve the dense, complex starch structures without rapidly off-gassing. This slow process contrasts sharply with what happens during the Reich phase of our timeline, where those starches have broken down and fructan accumulation reaches its peak. Fructans belong to a category of carbohydrates known as FODMAPs, fermentable oligosaccharides, disaccharides, monosaccharides, and polyols. Gut bacteria ferment these specific molecules very rapidly. Because the fermentation of fructans happens so quickly, it generates a significant amount of excess gas. For patients with hypersensitive irritable bowel syndrome phenotypes, this rapid gas production triggers immediate abdominal pain, bloating, and distension. Therefore, unripe bananas act as a highly specific, low FODMAP delivery vehicle for colon health, whereas ripe bananas are active high FODMAP triggers. The clinical efficacy of the pulp is entirely dictated by its phase state. Turning from the localized gut to systemic circulation, we must examine the agricultural waste, the peel. The working hypothesis in recent studies is that phytochemicals in the peel can act as a systemic anxiolytic by delivering tryptophan to the brain. To test this, researchers processed the raw peel powder using a standard laboratory extraction parameter, a 50% ethanol maceration, creating banana peel extract, or BPE. The first analytical step was to run a thin layer chromatography assay to qualitatively verify the presence of tryptophan in the resulting extract. Looking at these assay results under 366 nanometer UV light, you can see a faint purplish stain in the BPE spot marked A, which shares the exact same RF value as the dense tryptophan control spot marked B. While this qualitative test confirms that tryptophan does exist in the extract, the visual faintness of the spot suggests a significant quantitative failure. To find the exact concentrations, researchers analyzed the materials using high-performance liquid chromatography prior to extraction. The data revealed a critical discrepancy. The raw peel powder contained a measurable 0.10% tryptophan, but the 50% ethanol extraction yielded a negligible 0.02%. This severe drop in yield is tied to two specific biochemical limitations. First, tryptophan is highly susceptible to oxidation. Physical processing and storage of the peel degrade the target molecules before extraction even begins. Second, tryptophan exhibits extremely poor solubility in a 50% ethanol solvent matrix. The chosen chemical environment was simply incapable of pulling the remaining amino acids out of the raw biomass. Even though the raw peel contains the necessary anxiolytic precursors, standard processing protocols destroy or fail to isolate the target molecules. The resulting BPE is rendered clinically useless for neuropsychiatric intervention. This leads us to the secondary pharmacological hypothesis. If the extract fails to deliver tryptophan, can it still mitigate stress-induced depression through the scavenging of reactive oxygen species? To evaluate this, researchers used the DPPH assay, the standard in vitro mechanism for measuring free radical scavenging capability. The assay relies on electron transfer. When a DPPH free radical accepts an electron or a hydrogen radical from an antioxidant donor molecule, it stabilizes. The assay measures how effectively a sample drives this chemical stabilization. The quantitative metric of success for this test is the IC50 value, the concentration of a sample required to scavenge 50% of free radicals in the solution. This data table compares the IC50 of banana peel extract against a known pharmacological baseline. Standard ascorbic acid, or vitamin C, hits the 50% threshold at just 3.62 parts per million. The BPE requires a massive 684.69 parts per million. Translating this data mathematically, the BPE requires roughly 180 times more concentration to achieve the exact same antioxidant baseline as vitamin C. This demonstrates incredibly weak activity. This failure presents a notable data anomaly regarding total phenolic content. Testing confirmed the extract did contain a seemingly adequate 17.41 gallic acid equivalents per milligram. However, the Pearson's correlation test returned a value of negative 0.269. This negative value proves there was no significant statistical relationship between the extracted phenolics and actual free radical scavenging. The mere presence of phenolic compounds does not guarantee physiological antioxidant activity. In the case of this specific extract, the ROS scavenging hypothesis is entirely dismantled by the data. Bringing together the findings from the local gastrointestinal analysis and the systemic pharmacological testing, a strict chemical reality emerges. When we map the two divergent functional pathways analyzed in these studies, we see completely separate outcomes. On the gastrointestinal side, the clinical application is highly successful. Unripe pulp provides a highly specific, targeted delivery vehicle for IBS management, utilizing its dense resistance starch matrix. This localized action bypasses systemic absorption to safely produce short-chain fatty acids without rapid fermentation. On the systemic side, the data proves that theoretical potential locked inside raw agricultural biomass does not automatically yield an efficacious extract. Standard 50% ethanol maceration yields a peel extract with negligible tryptophan and weak antioxidant capacity. Its current theoretical use as an anxiolytic is invalid. To actually unlock the peel's bioactive potential, future extraction protocols require optimization using alternative nonpolar solvents like chloroform or acetone. Botanical interventions are not monolithic cures. Their clinical validity is entirely dictated by precise state matching, rigorous ripening timelines, and strict biochemical processing.